Wow. Exciting. Oh, that's fine. I wasn't too bad. Hi, Ross.
Oh, yeah. Yeah, sure.
All right, well, we'll get started. Good morning. Welcome back. Our first talk this morning is by Lyons from Indiana University on Voronoi tessellations without nuclei. And I guess I'll also say if you have questions during the talk, I can interpret for you with the mic, or I can hand you the mic, whichever you prefer.
Thanks very much. In fact, I will also have questions for the audience. And so please use the microphone as well to answer the questions as I go, because I like to have audience participation, especially because I can't see you. It will help me to know how well you're following. Thanks to the organizers for inviting me to speak. I'm giving another talk on a different subject tomorrow morning. And I'm talking about tessellations of a certain sort. These tessellations are sometimes also called mosaics. And that's why I chose that particular image of the University of Texas Tower that you see there. This is based on work of my former PhD student, Sandeep Bhupatiraju, who is actually has joined us from India right now via Zoom, and joint work in progress with 4 people in Paris: Matteo da Cayley, Nicolas Curien, Nathanael Enriquez, and Meltem Unel. So what are Voronoi cells before we talk about anything random? Here you have some black dots, which are points in the plane. And there are colored regions where each region corresponds to those points that are closer to the nucleus in there, that dot, than to any other nucleus, which are the other dots. And how are these formed? You can just start by growing spheres at the same rate, which stop when they meet another sphere. And of course, they will meet at the bisectors, at portions of the line bisectors between any 2 nuclei. So those are the Voronoi cells. This can be in a finite region or an infinite region. In fact, in any metric space. Are there any questions on what Voronoi cells are?
No.
Okay. So the next thing is, where are we going to put these nuclei? They're going to be coming from Poisson point processes, which you've heard about a little bit in Marcos's talk the other day. Let me just remind you what they are. So they're defined by these 2 properties down here. If I have any region A, the absolute value A denotes the area or volume in any dimension, times lambda. That's the expected number of points in A. And if I have disjoint regions, the numbers in those different regions are independent. Now, how should you think about this intuitively? Actually, you can do it by approximating. You divide up into small little regions. They don't have to be equal squares or equal areas even. And then when the size of the region is very small, you just put a point in there with probability lambda times its measure. Then you take them smaller and smaller and keep going like that. And you get some random scatter of points. So you should think about it as a limit of Bernoulli distributions of points in very tiny areas with a very small probability of being in a point in any of those regions. Okay. Now, so let's look at the Voronoi cells associated to a Poisson point process in Euclidean space. And what we will be looking at for the entire talk in other settings is what happens when the intensity, that constant times the volume of a region, tends to 0. Now, the simplest way to understand this in Euclidean space is to sample the nuclei with intensity 1, which are here in red dots. And Voronoi cells are drawn there with black edges. And we will dilate. In other words, multiply each vector by some constant. So dilating around away from the origin. Why does that work? Why does that give a valid sample from a smaller intensity? Well, when you dilate, all lengths will be multiplied by that factor. And so all volumes will be multiplied by that factor to the power d if d is the dimension. But the points are staying the same. Therefore, the intensity of point per area or volume is going down by that dilation factor to the power d. Okay? So rather than resample with a lower intensity, we'll keep the same sample and then just dilate. So what happens when we do that? I'll show you a movie. Okay, so what happened? All the nuclei disappeared to infinity, of course, because they were dilating away. But as well, the cell of the origin became the only cell that you could see. And in the end, there are no nuclei and just one cell. It's a completely trivial limit. Uninteresting and boring. Okay? But that turns out not to be the case in some other settings. So we're going to look in this talk in discrete settings and continuous settings. The discrete setting in some ways is simpler technically, in other ways more complicated. But let me start with the discrete setting. So fix an infinite connected graph, like here is the standard graph of z squared. And let p be between 0 and 1, and now consider Bernoulli p process on the vertices. In other words, place a nucleus at each vertex with probability p independently across different vertices. Then form the Voronoi cells of the nuclei. Now, because this is a discrete setting, there may be ties of distance, and so break them in some fashion, which we'll get to later. And this gives what's called the random Bernoulli-Voronoi tessellation. So as p tends to 0, will there be a limiting non-trivial tessellation? What setting will we look at? We want to look at some settings with some regularity. So for example, Cayley graphs of groups will be very nice. Here is the Cayley graph of z squared with the two generators, 1, 0, and 0, 1. So that means that these two elements of z squared generate the whole group in the sense that the smallest subgroup of z squared that contains them is the whole group. And this is the Cayley diagram, which is the Cayley graph where you take an edge between any two vertices when you can get from one to the other by multiplying by a generator. And it makes it a diagram by we've actually labeled it with the generator and the orientation of which way the multiplication goes. Now, this does not have these nice continuous dilations like we have in Euclidean space. And it'll be useful to think of this another way anyway. So let b sub n be the size of the ball of radius n about a fixed vertex in this Cayley graph. So distance is just measured by the shortest path distance. Orientation has nothing to do with the edges. In z to the d, for example, b sub n is of order n to the d. Suppose, like in z to the d, we have that the size of the ball of radius n plus 1 is comparable to the size of the ball of radius n. The quotient tends to 1. Then I claim that the limit of the Bernoulli-Voronoi tessellation as p tends to 0, is the trivial one, boring one, consisting of just one cell. So how do we see that? Well, how close is the nearest nucleus to the origin? Basically, you have to go, since p is small, to a distance where you will see roughly 1 over p vertices that might be a nucleus. So b sub n should be comparable to 1 over p. Now, because of this assumption about the asymptotics of the sizes of the balls, if we go some fixed k and we add some fixed k to the radius, then b sub n plus k minus b sub n is little o of 1 over p, because of this assumption here, for each fixed k. Now that means if you go an additional distance k, it's unlikely that you're going to pick up another nucleus. So in other words, the next nearest nucleus to the origin has a distance much greater than n with high probability. Now, what does that mean about the vertices within some fixed distance of O? They're very likely to belong to the same cell as O for any fixed distance. Okay, so that is the reason why all vertices in the limit will belong to the same cell as the origin. Any questions on that?
Nope.
Okay. Now, this is the case where we have this nice relationship, but of course, this is pretty special. Let's look at first greater generality about the exponential growth rate of the sizes of balls in Cayley graphs. This limit always exists. Why? Suppose we look at a ball radius m plus n. I claim we have the simple inequality. That is the most b sub m times b sub n. Why is this? If you go to distance m plus n, any vertex at that distance, at most m plus n, we could go back to the origin and find a place within distance m of the origin, and then go at most distance n from it. Now, balls around any vertex look the same as around any other vertex. Cayley graphs are transitive, just as the picture that you saw. And therefore, this is an overcount. B sub m times b sub n counts probably more than once every vertex within radius m plus n of the origin. So this sub-multiplicative property, if we take logs as sub-additive, then is used by Feketa's lemma to give this limit existing. So that's a simple elementary fact. Now, suppose we have that the limit of the ratios of successive ball sizes exists and some number alpha. Then this exponential growth rate is also alpha because b sub n is just a telescoping product of these ratios. And so there's n of those ratios, and we raise it to the power 1 over n, that will tend to the same limit. However, this sub-exponential growth, where this limit is 1, might not be the same as the assumption we made above. In fact, it's unknown, unfortunately, for Cayley graphs. So that's just an indication of some of the subtleties of geometric group theory that play a role in understanding what happens for the limits of Bernoulli-Poisson, Bernoulli-Voronoi tessellations in Cayley graphs. Let's look then at a case of exponential growth. The simplest case is a 3 regular tree. Almost every single talk in this workshop or summer school so far has mentioned trees, and I'm not going to be an exception. So here's the 3 regular tree. The vertices haven't been drawn, just the edges. And I drew this in the hyperbolic plane because it's a nice way to draw it and it'll be useful later. So let us look at the Bernoulli-Voronoi tessellations with a small intensity in a 3 regular tree. What I've done here, right, what Sandeep did, took this from his thesis, P equals 1/20 here is the cell of the origin, and P equals 1/200 here is the cell of the origin, and a random sample. Now, hope you can see that there are two colored vertices. One is colored red and one is colored blue. Here's the red one here, and here's the blue one here. One of those colors means it's the root of the tree, just some fixed vertex. And the other color means that is the nucleus of the cell of the root. So my first question for you is, can you guess which color represents the root and which color represents the nucleus? Hoping to get an answer.
Red is the root, blue is the nucleus.
Red is which?
The root.
The root. Why is that?
Well, because I guess at least on the one on the right, you can see that like it's all the way at the end, and so like it would be, if that were the like nucleus, then that would mean that there's like two other nucleuses attached to that root also, which makes it so that there are no cells close to it, and that would be quite rare, I would expect.
I couldn't hear too well, but what you said, but I'm guessing that you said the right thing, which is, yeah, you definitely compare to the blue, right? Yeah, on the left, of course, it's hard to tell. They don't look much different, but you see a big difference, as you said, on the right. This one, the red one, only has one neighbor. The blue one has three neighbors, and they all go pretty far. And that's the way it should be, right? A nucleus gathers all the vertices closer to it than to any other. Very low density here. And so it should have a lot of vertices that are closer to it than any other. And in this case, the root happened, to be there were none even further from this particular nucleus in the same cell. That didn't have to happen, but it happened. Okay. So that's right. Now notice one other thing, which keep in mind for later. What is the distance between the root and the nucleus? So here it's 1, 2, 3. Here 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So it's 3 with 1/20 and 9 with 1/200. So I want to keep that in mind for what we're going to, the quantitative analysis we're going to do. So our question is there a non-trivial limit as p tends to 0? And this picture might indicate that there should be, because the root in particular only had degree 1 in that simulation. Okay, so now we have to discuss how we're going to break ties. So in addition, we'll give one more piece of information. Each nucleus will label with an independent uniform 0, 1 random variable. And then if there are any ties, the smallest label wins the tie. That's the nucleus that will get that vertex. Okay. Now, if we want to know whether there's a non-trivial limit, we want to look at an edge and see whether its endpoints belong to different Voronoi cells. If it never happens, or the probability tends to 0, then you only have one cell in the limit. So when does it happen? Well, it'll happen if the distance from one endpoint to its closest nucleus is the same as the distance from the other endpoint to its closest nucleus. Now, here's where I said, keep in mind how far that closest nucleus is. As we saw in the beginning with the Euclidean lattices, or z squared, the closest nucleus should be at a distance where the ball of that distance is of size, cardinality, roughly 1/p. Now here, this is the 3 regular tree. The ball at distance n is of size roughly 2 to the n. So if 2 to the n is roughly 1/p, n is roughly log base 2 of 1/p. In the example, for example, p was 200, 1/200, 1/200 is 200, and log base 2 of 200 is not that far from 9. Okay. So in this case, there is a reasonable probability of having one of the endpoints at that same distance to the other. Sorry, just a second. Yeah, and so if we look at that edge, one endpoint is a roughly distance log 1 over p, and the other endpoint will also have a reasonable probability by similar calculation, you can do it exactly, of having a nucleus at that exactly the same distance. So therefore, that edge will join two different Voronoi cells if that happens. This probability does not tend to 0. And so the Bernoulli-Voronoi tessellations do not have a trivial limit as p tends to 0. You can consider limit points before we find out whether there's an actual limit. And all limit points are non-trivial because not only does this not tend to 0, it stays bounded away from 0. Okay. But the question I want to look at is, do they have a limit? Now, every limit point is still kind of nice because we start with a tessellation by these finite cells and take a limit as the intensity of the nuclei tends to 0. So before we take a limit, obviously, the entire tessellation is invariant under all automorphisms of the Cayley graph. So those are already kind of nice. And these are then limiting Bernoulli-Voronoi tessellations without nuclei. If there is a limit, that would provide a canonical choice of such a process. So there is a limit on regular trees as p tends to 0. So this was a major theorem in Sandeep's thesis. And the proof is quite complicated. He calculated all elementary cylinder probabilities and showed that they are polynomials in p. And therefore, they have a limit as p tends to 0, just the constant term. Why would they be a polynomial? There are infinitely many ways to form cells depending on the closest nucleus. The closest nucleus is very likely to be at a certain distance, but it could be at any distance. So you have to sum over all infinitely many possibilities. And it turns out that the sums in all cases telescope. So all I'll say about the calculation is to say a bit about this picture from his thesis. Here, an elementary cylinder event was these two edges are present. They know their endpoints belong to the same cell. These dashed ones are not present, and then these ones in separate colors are present, and so forth. And so in order to calculate the limiting probability of this, he had to organize the calculation very carefully. And in fact, these portions of cells had to themselves be organized in a little tree. So it was a very, very long complicated calculation. And but because he could calculate all the elementary cylinder properties, he could calculate a lot of interesting probabilities. But I don't think I have time to give you examples. So let me skip. Okay. Let me tell you one property, though, of these limiting Voronoi cells, which I'll call ideal for reasons which will come up later. And the claim is that each of the limiting ideal Voronoi cells have just one end. Now, I think you've heard about ends before in Tom Hutchcroft's talk at the beginning. An end is easy to describe in a tree. A tree has only one end if from each vertex is only one semi-infinite path. So proposition, each ideal Bernoulli-Voronoi cell has only one end, almost surely. So why is this? Well, we'll go back to what we're talking about here. I'll let the degree be d instead of 3, but you can take d equals 3 if you like. For positive p, the closest nucleus, now how close is it actually the distance to be within this number n I talked about before? It's actually exponentially likely. Why is that? Well, the balls are growing exponentially fast, And to be at a closest nucleus at that distance, that means inside there have to be no nuclei. So that's 1 minus p to this exponential power. And then you have to have one at that distance, which is p to that exponential power. So as the distance n changes, you're going to have exponential growth or doubly exponential decay. And therefore it's exponentially likely to be really within an additive constant of this n. So consider the root and x, and so they have the nucleus at some distance. Now look at the opposite distance. We want to know whether there's another end. So this, you think about this nucleus is going off to infinity. That's going to be one end. If there's another end, then from the other side, you have to have further and further distances that belong to the same cell. So consider a vertex x in the opposite direction at distance r from O. So x will belong to the cell of O, if and only if nu, the nucleus of O, is the closest nucleus to x, which means that vertices closer to x than now r plus n are not nuclei. So how many such vertices are there? Roughly d minus 1 to the power r plus n. So using what n is, this is d minus 1 to the r over p. So such vertices are not nuclei with probability roughly 1 minus p to this number. Now 1 minus p to the 1 over p is less than or equal to e to the minus 1. So this is a bound for the probability that you don't see another nucleus that could absorb this vertex x. How many such vertices at distance r do we need to consider? About d minus 1 to the power r. So d minus 1 to the power r times this is a bound for the probability that you don't that this vertex x that you don't see another vertex x at distance r from O in the opposite direction, and that doesn't depend on p and goes to 0 as r tends to infinity uniformly in p. So therefore you don't have a second end in a limit. Any questions on that?
We're good.
All right, thank you. Now, briefly, what about other Cayley graphs than regular trees? So this is a Cayley graph of the modular group Z mod 2 star Z mod 3. And the way it looks is I took the 3 regular tree and every vertex is just changed to a triangle. So these are Z mod 3 edges and these are Z mod 2 edges. Looks very much like a tree, right? Well, actually, Sandeep proved that the low intensity limit on this Cayley graph does not exist. Let me give you a very brief idea of the proof. You consider one of those Z mod 2 edges and the probability that it joins 2 vertices in the same Voronoi cell. That limit does not exist. Why? Well, you have to do this infinite calculation. Turns out you don't get a telescoping sum. You need to analyze this sum, q is 1 minus p. As q tends up to 1, does this limit exist? No, it doesn't. Not obvious that it doesn't, but it doesn't. And that's what turns out to be the case. So there are some complicated, I mean, simple in principle, but complicated in practice calculations you have to make. So we actually have an open question. Are there any Cayley graphs besides trees that admit non-trivial limiting Bernoulli-Voronoi tessellations? We don't know. You can see Sandeep's thesis for more information about that question. So that's the end of the discrete part. Now I'm going to go to the continuous part.
I have a question.
Yes.
What's the growth rate of that group?
Z mod 2 star Z mod 3?
Yeah.
I don't remember offhand. It's not too hard to calculate.
Is it exponential or not?
Oh yeah, it's exponential. Sure.
Okay.
Yeah. See, I mean, it's basically 2 to the n, but it's modified a bit because you have to, go along these triangle edges. It should be probably square root of 2 to the n. And in other words, 2 to the n over 2. Square root of 2 to the n is probably what the growth rate is. Yeah, I think that's what it is. have to check carefully.
I have a question, Russ. I want to, so, okay, the limit doesn't exist, but because of compactness, you do have limit points.
Right.
no? So do you know what the limit points are, or?
No. Yeah. So of course, these limit points in some sense, like I said, are nice because all of them are invariant under all automorphisms of the Cayley graph. But no. So yeah. And so no, they haven't been analyzed. For example, you could try to prove at least qualitative properties, like they all have one end. So that would certainly be worth doing, but no, none of that has been done.
Thanks.
No. Any other questions?
Yes.
I guess probably I don't know how much you would know about these limit points. It sounds like not a lot, but like if it's a invariant under the group action, do you know anything about like ergodicity of these, whether it should be limit point should be ergodic or
Yes, it should be ergodic and even better, strongly mixing of all orders, and have a spectral gap. Yeah, all those nice things.
thanks.
Okay, I think that's it.
Okay, thanks. Okay, so now I want to tell you about the continuous setting of hyperbolic space. So let me give you just a brief introduction to the geometry, how you should think about it, mostly by pictures. So this is a three-regular tree. And the nice thing is that all edges, so this is a Poincare disk model, all edges here actually have the same length. Here, it's a tiling by pentagons that are regular and all congruent. Okay. So that gives you some idea. You can see there's exponential growth. More precisely, the metric using a complex number z is 2 times dz over 1 minus absolute z squared. So as z gets close to the boundary, the metric blows up. Now, very nice thing about this model is angles are Euclidean. What you see by your eye is true angles. So for example, for these pentagons, these are regular pentagons, all angles are 2 pi over 5. Now, geodesics, shortest paths, are Euclidean circular arcs that meet the unit circle at right angles. The unit circle is at infinite distance. It's called the ideal boundary. That's why the word ideal comes in. So if these geodesics were extended all the way, they would meet at right angles, okay? Now, there's also an upper half plane model, just what's above the x-axis. And the metric here has this form, absolute dz, over the imaginary part of z, the distance to the x-axis. Again, angles are Euclidean and geodesics are Euclidean semicircles. Here's a fact to keep in mind. If I have a geodesic triangle, the area is pi minus the sum of the internal angles. Okay? All right. And a similar thing in higher dimensions. I won't mention here exactly what, but there's some powers that come in. Otherwise, it looks the same. So here I'll just show you a picture of the upper half plane. It's a transformation of an Escher print by Arkadiusz Jacek. And you can see as you get close to the ideal boundary, these angels and devils get tinier and tinier. Okay, so that's how you should think about hyperbolic space. Now, here is a Voronoi tessellation where we put in these nuclei, they're kind of small, with a Poisson point process of some intensity times the area measure. And then you see the lines, which are geodesics, that's split at equal distance, okay? Now, we want to let the intensity of the Poisson point process of the nuclei tend to 0. We cannot just have a simple dilation like in Euclidean space. There is no dilation that preserves ratios of distances. However, you can dilate to preserve ratios of areas. And because areas are what matter for the law or the sample of the Poisson point process, we can do that. So let's see what happens. And let me know if the movie is not coming through smoothly. You should see the nuclei going off to infinity, and the tessellation becoming thinner because we really won't have enough information to give additional parts of the boundary of the cells. The cells do get infinite, but as you can see, they seem to stabilize. Okay, now I'm going to show you something else. The vertices of the Voronoi tessellation have degree 3 with probability 1. You won't see 4 points at the same, on a circle. And if you, so you can make a little triangle out of these nuclei that are the closest to some vertex. And you get this, these are called the Delaunay triangles. And we could dilate them in the same way. I mean, just show what happens when we do a dilation of the nuclei for this, for the Delaunay triangles. So you can see where you have these high degree vertices, those are the nuclei, right? All vertices of the triangles are nuclei, they're going off to the ideal boundary. And it looks like in the limit, we get this nice tessellation of the entire hyperbolic plane by these, now that these are called ideal triangles. The vertices of these triangles are at infinity. Okay. So the limit does exist, and we can actually describe it. And so this is one of our theorems. Briefly, why does the limit exist? It's like what you see in the movie. Look at the origin, say its closest nucleus, all the nuclei dilate, will be eventually, it'll just be one of those nuclei as it moves away. And because we start with an isometry invariant process, then as you take a limit, you also have an isometry invariant process. So this will be the ideal Poisson-Voronoi tessellation nuclei. Now, we can actually describe the limit exactly and therefore analyze a lot of things more easily than in the case of the tree, actually. So first, let's describe this dilation process. I have to give you some more quantitative information. The ball of Euclidean radius r, centered at the origin, is a ball of hyperbolic radius log 1 plus r of 1 minus r, which is roughly log of the inverse of 1 minus r. So the hyperbolic volume of this ball, it grows exponentially. It's some constant roughly times 1 minus r to the 1 minus d as r tends to 1, exponential in the hyperbolic radius. So suppose we start with a unit intensity Poisson point process of nuclei in h to the d, so now allow d dimensions like I did here, coordinatized in the unit ball model with an angle in the unit sphere. You can think of, again, d equals 2. This is just a circle, and radii in increasing order. Now, when we dilate, the angles don't change, just the radii increase. But it turns out, we needed to pay attention only to the volumes that are associated with them. And you get, if you scale properly by the volume, a Poisson point process of unit intensity in the, what we call the corona. So the angles times these positive real numbers. That's what this turns out to be. Then you can form the ideal Voronoi cells directly, instead of talking about limits. Now, you can't talk about distances because things are infinitely far away, but you can talk about separation. So the way you measure separation from a point z in the unit ball to a point theta comma t in the corona is this formula. These are Euclidean distances, z minus theta squared over 1 minus c squared times t to the 1 over d minus 1. If d is 2, this is just t. Point is, there's a specific simple formula involving just Euclidean quantities. So here's a picture showing what I just mentioned. Here's the corona. There are 500 nuclei. Of course, we need infinitely many, but only 500 here. And what is shown by the distance to the unit circle outside is the point, the radius scaled, and the angles aren't changed. And so they just are lines joining up with the angles. And here is the portion of the Voronoi tessellation in black. And in blue is the Delaunay triangles. Okay. Now, separation was used to measure these things. So here's the separation field. From any point in the disk, there's a closest nucleus and a separation from that point to its nucleus. And so that's what's plotted here with this temperature scale. Now you can see something. These points where the separation is maximum, goes down on most sides, are the boundaries of the Voronoi cells. These are singularities of the separation field. It's not differentiable. And then where three meet are the nuclei. Now, there's something interesting. There are many interesting things to look at. I've just drawn the nuclei here and the Delaunay ideal triangles. Each nucleus corresponds to one of these Delaunay triangles, right? It's three closest nuclei, ideal nuclei. And so I've just drawn a matching to the in-center of the Delaunay triangles here. The guarantees, this is this blue around the boundary. Inside of this, it's guaranteed that what we have done of the Voronoi tessellation, which I haven't drawn, I've only drawn the nuclei here, is correct. Nothing can change it by looking at more than the 500. Okay. So again, each cell has one end almost surely. Now, what does it mean that these cells have one end almost surely? If you look at the boundary, that means the boundary is connected, and the vertices have degree 3 almost surely. All the cells are infinite, which means the boundary edges form a 3 regular tree almost surely. It's very nice. So it's a canonical embedding of the 3 regular tree in the hyperbolic plane. So we've calculated various things about it. Why do they have one end? Well, before I go to that, I'm running out of time anyway. So here's the 3 regular tree I've shown before. There's another 3 regular tree, which is a dual of the Delaunay triangulation, which I've drawn in orange here, still with the matching. Now, there's some, and here is just a portrait of a single cell, the cell of the origin, where the nucleus is always at the top, to give you some idea of the variety of the distribution, in other words, of the cell. Here's in 3 dimensions. I actually have a movie, but there's no time to show that. So it looks similar if you want. We can compute one cell. I'll have to go kind of quickly here. Compute one cell. And how do we determine its properties? So the ideal nucleus in the corona of the cell of the origin is the one with the smallest radius. So theta 1 T1. And the points in that cell are those whose separation from that nucleus, ideal nucleus, is less than the separation from the other nucleus. So I had a formula, comes out to this. You can cancel these denominators, put this over on the right-hand side, and you get this. So we're looking for point Z in the cell of the origin. They're the ones that satisfy this. For all n, this number here is bigger than 1 because Tn is bigger than T1. If I have this theta n fixed and theta 1 fixed, what is a set of such Z? This was known to Apollonius. Points at a given ratio from 2 foci form a circle in case of Apollonius or a sphere in higher dimensions. So these are the points outside all such Apollonian spheres. So you can calculate them directly, immediately. And if we now want to do calculations, it's easiest to do it in the upper half plane, upper half space or model. And it turns out that if we put the ideal nucleus at infinity, that's one of the points in the ideal boundary, and the origin at 0, 0, 0, 1, then the cell of the origin is what's outside hemispheres with certain radii and certain centers. These are random radii, random centers. These are points of a Poisson point process in the upper half space. with not a constant intensity, but this measure of the intensity. So as rho tends down to 0, it blows up. But you also have to exclude all the points that fall above this hyperboloid. And ED is a random variable. The cell, okay, so it turns out that's how you can calculate it. This hyperboloid restriction is a little bit annoying, but there's another interesting thing about it. There are only finitely many that would fall in here anyway. So you could ignore those if you want to know what happens most places, all about a finite region. And so actually the cell boundary differs in only finitely many faces from the distribution given by removing this restriction. And if you remove this restriction, then you get a process which is stationary with respect to translations or rotations on r to the d-1, the ideal boundary. And this makes it easy to calculate. So this is actually still with our hyperboloid restriction. So this is seeing a portion of the boundary of the cell at that point origin, okay? So what's above these hemispheres? And there are a bunch of hemispheres you can't see that are tinier below these ones. So you can use these calculations to prove this one-endedness. I'll just say quickly, it's similar to the proof sketch I showed you for trees. And now we want to show that these hemispheres, which get tinier and tinier, cover the ideal boundary almost surely, which means there won't be another way to get to infinity. Okay, so here's just a quick portrait of the ideal Poisson-Voronoi tessellation, of the ideal Poisson-Delaunay tessellation. And a quick statement about similar ideas have been used by some other people to prove interesting theorems. And finally, I want to say, if you remember from my abstract, Poisson and Delaunay, but especially Voronoi and Delaunay tessellations are used all over the place, and especially in science, engineering, and mathematics. But I mentioned even in baking. So now is the time to tell you about the baking. So here is a Ukrainian pastry chef, Dinara Kasko, and a quote from Verve magazine, which had an article about her. Employing mathematical principles such as triangulation, the Voronoi diagram, and biomimicry, Kasko puts immense thought into each of her creations and constantly strives to innovate by drawing on her past architectural experience. She had been an architect, but changed to become a pastry chef. So here's an example of one of her cakes. I think you should recognize what this has to do with Voronoi tessellations. If you cut it, you can see what's inside. Looks more like a cake. Okay, so that's it. Thanks for listening. Bon appetit. Smacznego nova. I'll take any questions.
Okay, questions for Ross? I have a question. You had like a video you said of the like ideal cell in like 3 space, maybe?
You said that I said that I had a video?
Yes, you had a video that you said you didn't have time to play.
Right. You wanted to see it?
Yes.
Okay. Yeah, I also have the cell video of that boundary. So I should have opened this up beforehand. I thought there wasn't going to be time. So it's taking a little bit of time to open. You see this opening?
Yes.
Okay. Okay, so here it is. So I can rotate it around and show you various things about what it looks like. I mean, it's not really it's a video as much as something you can manipulate. And it's online. Anyone can do this. So, okay.
Yeah, thank you. Where can we find it online?
Yeah, well, let's see. Okay, maybe I can put this in the chat. Oh, well, that's
Sure.
not going to help very many people.
Well, you can put it in the chat and then we can put it somewhere.
Okay.
available.
So let's see, let me open the chat. Oh, maybe I didn't copy it. Oh, there
Hi,
we go.
Russ.
Okay,
My question's maybe not so well posed, but so so you have this Voronoi cell, and you might compare it with horospheres that are that have the same point on the ideal boundary. And so if you
you might compare it with what?
with horospheres or horoballs
Horospheres. Yeah,
that are
right.
that have the same point on the ideal boundary.
Uh-huh.
And so I guess what I imagine is that, for example, if you considered some horoball that had the same point on the ideal boundary, and you looked at the Voronoi, the portion of the Voronoi cell that lies outside of the horoball, you would see a bunch of clusters or I don't know what to call them, but a bunch of kind of bubbles or something, bunch of disconnected regions. Would you have some description of, I don't know, I'm just trying to understand what the landscape looks like, because it sounds like you have this very complicated surface, and it might be natural to compare it. I guess what I would like to say is that you have some kind of height function, right? Like
Okay,
height
so-
above or below a specific horosphere.
Yes, so I think I can answer your questions in a few ways. First of all, for those of you who don't know, horospheres are Euclidean spheres that have inside hyperbolic space that touch the ideal boundary, tangent there. And in the upper half space model, they're just planes parallel to the ideal boundary. So that's why I brought up this picture again. You could just imagine a plane parallel to this. These hemispheres that we put down, you have this, translation invariant and rotation invariant law. So no matter how high you put your horosphere, there will be points, there will be hemispheres that go above it. And then there's everything else below it. And because we have such a actually relatively simple description via this Poisson point process of hemispheres, we could calculate many things of the type that you're asking about, I believe. And although this is kind of complicated and it came from hyperbolic geometry, horospheres themselves are flat, they're Euclidean, as it looks like here. And this surface, even though it's not Euclidean because it has all these hemispheres, which are geodesic totally geodesic hemispheres, is basically Euclidean. And for example, if you look at what you're seeing are the two-dimensional faces of the boundary of this cell, right? That's what you're seeing here. And you could ask how many sides, how many edges lie on those faces. Of course, that's random, but an expectation at 6, just like you have in the Euclidean plane. And the reason that, so even without all this analysis, the reason you should expect it to be Euclidean is the following. Before we take a limit, we have these cells in hyperbolic space. As intensity goes down, the cells get bigger, but they're still finite. They are approximately spherical or ball-like, very approximately. And a sphere in hyperbolic space is also a Euclidean sphere, a large radius, so it's getting closer and closer to being flat. So you should expect that the boundary for the ideal cells will also be governed by Euclidean properties in some sense. So I know that was not exactly what you're asking, but it should indicate that we can answer these kinds of questions, because with this description here, we have a very good understanding. So The stationary distribution is what you see outside of some finite region. So for all asymptotic properties, you can just look at the stationary region. Another way of saying that is what happens when we go closer to that ideal nucleus of that cell. We see what happens here in a pretty simple description.
Well, thanks.
Okay, let's thank Russ again for a great talk.
Thank you. Oh, by the way, I wanted